फुल स्क्रीन अच्छा फुल स्क्रीन ना just total screen টা share যদি then it makes it easier share okay full हाँ full no top একটা desktop হ্যাঁ share হয়ে গেছে yeah yeah उसको हटा दो बीच से हाँ perfect thank you okay so I welcome everyone for this edition of the Wednesday Colloquium post Diwali. I hope you had fun with your crackers. So it's a pleasure to have Professor Urbasi Sinha all the way coming from Raman Research Institute to our institute for this Wednesday Colloquium. I will let Vijay introduce Urbasi formally, but just for Urbashi's sake, the colloquium has a tradition. It was started by our founding director, Professor Homi Bhabha, and it allows for everybody in the natural sciences faculty to come and listen to an eminent expert. So thank you for doing this for us today. And I will let Vijay introduce formally Urbasi.
Thank you, Jyotishman. It's my pleasure to introduce today's speaker. Urbasi and I know each other for many years now. So Urbasi Sinha is a professor at the Raman Research Institute in Bangalore and holds a Canada Excellence Research Chair at the University of Calgary, Canada. At RRI, she heads the Quantum Information and Computing Lab and is also an associate faculty member at the Institute for Quantum Computing in Canada. Urbasi completed her PhD and MSc in physics at Cambridge University as a Gates Cambridge and Nehru Chevening Scholar, respectively. Her postdoctoral work was at the Institute for Quantum Computing in Waterloo, Canada, and focused on quantum optics experiments. Highlight of the work she did there was the triple slit experiment, which serves as a precision test of the Born's rule for probabilities in quantum mechanics. She then returned to India in March 2012 and set up the Quantum Information and Computing Lab at RRI Bangalore. Her research focuses on quantum information processing, secure quantum communication, and quantum computing, and covers both technological applications and also tests of fundamental quantum phenomena. Her group recently demonstrated a secure scheme for semi-device independent quantum random number generator by utilizing the Leggett-Garg inequality violations. Her research group also demonstrated a quantum communication channel between fixed and moving platforms in 2023. Urbasi has received various awards and recognitions, and which include the Homi Bhabha Fellowship in 2017, the ICTP ICO Galliano Denardo Award in 2018, and a recognition by the Asian Scientist magazine as being among the Asia's top 100 scientists in 2019. She also received the Simons Emmy Noether Fellowship at the Perimeter Institute for 2020-2023 and led the winning team at 2020 BRICS Future Skills Challenge in Quantum Technology. Recent honors include the Asocham Women in Cyber Award in 2021, the SIES Chandrasekharendra Saraswati National Eminence Award in 2023, a Distinguished International Associate Award from the Royal Academy of Engineering, UK in 2024, and most recently, the Rashtriya Vigyan Puraskar Yuva Shanti Swarup Bhatnagar Award from the Indian government in 2024. Urbasi has also played a significant role in formulation of the National Quantum Mission of India and will also be leading a team to develop quantum repeaters for quantum communication networks under this mission. Today, she is going to tell us about single and entangled photons and how they are used for various applications in quantum communications, quantum information, and quantum computing. Urbasi, welcome to TIFR, and we look forward to your talk.
Thanks a lot, Vijay. Can you hear me at the back? Yeah. So that was a very comprehensive introduction, and what I really liked is that Vijay actually did some homework as well. He just didn't read off from it. So I sort of forgive him for not inviting me for the last 11 years to TIFR. So the last time I came was 2013. I was going to start off with complaints, but I think he won me over, so I will not start off with complaints. So thanks a lot for inviting me again. This slide changer does not work, so I will position myself here.
Click with your mouse on the screen once.
Okay.
Then it should work.
Maybe we'll give up for now.
Okay, fine.
Next time, after 10 years, when I come back. Because it's not connected? Okay, so Jyotishman,
The second slide, that's the one.
Oh, this is the
This one.
Okay.
That's the one that should work.
so is it working, you think? So I think, in interest of time,
Let's take 1 more minute.
What in the interest of time?
क्या problem है? हाँ?
Support नहीं हो रहा है, छोड़ दो।
तो निकाल दिया ना?
ये चलेगा। विजय, छोड़ दो।
हाँ. So,
एक
काम कर रहे?
yeah. So
Yeah.
right and left.
Okay. Okay, so it's working. So Vijay is a good experimentalist. So thank you, Vijay. So the title of my talk is Light Camera Action. It's obviously going to be on photons. But the idea is that, as Jyotishman actually is a great colloquium coordinator, he sent a long email with exactly what to say and what not to say, and I read it. And so the hope is that, I learned something from you. And so it is going to be at a very general level, and hopefully, there are at least some people from biology here. Otherwise, it's a waste of time for you and Vijay and others, right? So I'm hoping that it's generic enough. And so it's going to be, touching upon what I did in the last 11 years with the hope that I'll again come back in 2020, when is it? 35. So that is the story. And so in order to start that, of course, we have to begin where we began. And this is December 2012, and this is the inauguration of my lab. Vijay kindly explained, about my work on the triple slit experiment. And so that is why I had 3 ribbons to cut for the triple slit. And these are the 3 co-authors, the senior co-authors in that paper. So it was all very symbolic of that experiment. And lots of people, here you see Gilles Brassard. This is, you can see him almost, yeah. So that is one of the Bs of the BB84 protocol, which is a very famous protocol in quantum key distribution. So what I'll do in the first couple of minutes is remind us that, all this new hype that we have, we are all contributing to the hype in quantum is actually, not so new. I mean, quantum has been around for much longer than the new things we say. And then, of course, justify a little bit about why we are excited all of a sudden once more. So it's not all hype. So that is going to be the main focus. And so this is, of course, something which still holds for me at least. But then I would say that nobody completely understands quantum mechanics, because if you don't understand anything, then we are not doing something right. And so this is the story which gives us all these very nice, impactful, applications of quantum. And these are all things I think all of us have seen for several decades. So nothing is new about this. So this is the idea that quantum is not a sudden new phenomena that has been entrusted upon us by the DST. It's getting recorded. So by the agencies to be. And so this is something which we are all familiar with. And it is also one of those things which has been really one of the most recognized fields in terms of pioneering contributions because of, the various prizes that people have won. And so this is a rich history and legacies of the Nobel Prize in Physics, for instance. So again, by no means new, and you, of course, know all about these prizes. And if you don't, just believe me that, quantum has had a rich legacy. So what is quantum, Vijay? I mean, and it doesn't matter. So, but then, this is a question we do ask ourselves a lot after all this. And so one of the things we can say is, maybe we have a little bit of an answer here with this thing that every object has a wavelength associated with it, which is inversely proportional to its momentum. So the larger the object, the smaller that wavelength. So for Sushil and me, if we were to go and hit ourselves against the wall, we will not tunnel through. The probability is whatever it is, you can calculate. So this is the point. So at some point, this becomes not so small, this probability. And then that is where the quantum phenomena actually start manifesting themselves. Otherwise, everything is quantum is what we famously say. But we don't see ourselves doing these weird things because we are rather large. No offense, you look exactly the same as 11 years ago. So rich history, lots of Nobel Prizes, it goes on. I won't bore you. I mean, I'm sure people already know these cases, and this is a very recent one in 2022, which of course we are very happy about specifically. It was given to, entangled photons, experiments, violation of Bell inequalities, and pioneering quantum information science. The pioneering people who motivate a lot of what we do. And so Alana Spage, John Clauser, and Anton Zeilinger. And if you're really interested in this prize, which you should be, because it represents a little bit of what our lab is working on. And if you don't want to read all the papers which led to it, it's a large number of papers which led to it. You can have a quick look at this article, which I wrote with a lot of time. And, so all the papers are there, and maybe it's not as badly written as you might expect from me. And so it gives you a story on this Nobel Prize in 2022. So having said that, If quantum has been around and already done so much, why are we so excited today? I'm sure, this Sushil was just saying almost every second student wants to work in quantum, which is a great thing. I mean, at least we'll have people to work with us for the national mission. But then what is it that is making us excited now, right? What is making us excited is we can do a lot more and dream much bigger. So all those applications I showed you, they were at a certain level. But now we have the ability to be able to go down to that single level, let's say a single qubit, 6 qubit for that matter, and be able to manipulate it, be able to measure. So these precision tools that we have developed over the last several decades in various fields now become very handy for actually being able to do what we call the second quantum revolution. So it's now being able to do a whole new set of applications which weren't there in that rich history that I kind of showed you. So there is a lot to be excited about, and it's not all hype. Just, sometimes that gets misrepresented. That is not true. So having said that, this is me, on a better day, looking better, a special award that I received in 2023. And this is, of course, my daughter. I mean, this is a standard thing. I mean, Sushil would understand, and Jyotishman, at that age group that our children are in, that is a normal expression, really. And so whatever you win, it doesn't really matter. And so this is the expression, but her expression has a reason behind it. And so the reason is why I get some salary. And so the reason is that both her parents, unfortunately, are physicists. And they have very interesting dinner conversations on experiment versus theory and so on and so forth. And she's also having the food along with us. She's our only child. And so as a result of which she gets to hear many things which other 12, 13-year-olds may not hear. And one of the things she keeps hearing is that her mother says that nothing will remain secure. I mean, award, no award, doesn't matter. She will not inherit anything anyway. I mean, and so this is a common conversation. And so why do you think, Sushil, I mean, you are of course from the field, do you think this is true? That, if we continue the way we do, that our children are not going to inherit anything? Not that we have a lot to give. We are, of course, scientists, and we do it because we love science and not because we can get rich. But then whatever little we have may not go. And so this is one of the concerns with how we keep data secure right now. Okay, and so she is not wrong in her thoughts. And so why is that? And now I come to my controversial slide, which is, Vijay versus, I don't know, I don't really see too many women. There are two beautiful ladies in the third row, whose names I don't obviously know. And so I would just say that Vijay must be very good with this situation at home. And you guys must be just generically good in this. Not that you want to be. I always aim for the left one. So there is a gender bias in the slide that, a certain gender, or all of us are very good in that, but some of us tend to pick up on the right side just because we want to live in a civilized house. Yeah. And so this is the situation. So now what am I saying here? I mean, it's not about clothes and ironing and household activities. This is an example of an everyday problem that is not equally hard both ways. And so, of course, one gender is obviously taking the easy route. So they do this very easily. But this is the reverse problem, and it takes longer. So the complexity of a problem is proportional to the amount of time it takes you to solve that problem, let's say, using whatever algorithm you have. And so the hardness of a problem, this is an example of a reverse problem, which is not equally hard both ways. And that's what we are using to keep our current data secure. For instance, 3 times 7, Sushil, 21. And then if I ask you the prime factors of 114371, don't answer. So factorization and multiplication are reverse problems, but they're not equally hard both ways. So that is an example of, this is the problem that is used for the RSA protocol. You are from computational science, I was just told. And so then obviously you know all this much better than me. So this is what we are doing for keeping data secure. And this is obviously a problem. So computational resources, they grow very fast, and today's hard problem could be solved tomorrow using brute force attack, classical or quantum. So whether it Shor's algorithm on a quantum computer which breaks factorization, or a very clever person who just comes up with an algorithm, there is no theorem which tells you that factorization is hard. It's just hard because we don't have the cure for it. So this is why my security should be independent of future advancements in computational power, new algorithms or new technology. It should be future secure. So whatever little we have should be available, in your case, 10 decades down the line, in my case, 1 or 2. So 2 more colloquia at TIFR. And so this should remain secure. And so this is what we are doing a lot in the lab, which is called quantum communications, which is a new paradigm where, our security is based on laws of nature or laws of physics or laws of quantum mechanics for that matter, and not on mathematical hardness of problems. So we ditch the whole idea of using a mathematically hard problem to come up with protocols, but use quantum mechanics instead to keep our data secure. And that is quantum communications and quantum. So I'll talk about it a little bit more because that's one of my focus areas. So we will discuss that. And then again, as I realize I do like little people. I mean, so obviously a bias there. So this is a little child with a teddy bear. I didn't draw this. So this is the artist. Okay. And so what am I depicting here? Gautam da. I mean, you seem like the artistic kind. I know you have an artistic background. So what do you think I'm depicting here? I mean, I'm not depicting anything. It's this very nice artist who has done this. So this is a gloomy picture where, this person is not very happy. There are no trees with any leaves and all the fish kind of are dead. And so this is a situation which we may be looking at if we don't do anything about what is happening to the climate right now. So this is a problem from the future, which could become very much our future. And so a future world if we don't take action now. So where am I getting to here? I'm supposed to talk on quantum, right? And so I have to, of course, praise the field that Vijay represents, which is quantum computing, of course. So now what can a quantum computer do? A quantum computer, I mean, that's the question that he gets asked a lot. What is it good for, right? I mean, of course, I'm not going to answer that for you. I have it much easier with communications. But then, even with that, with the small number of qubits that we have, we are able to run simulations for building new materials. So we can simulate new materials, which will be built by our colleagues from materials science, which can actually actively capture carbon from the atmosphere or the pollutant from the ocean. So these are actually use cases that are being done using current day quantum computers as well. And so this is a very interesting use case, which doesn't get as much talked about as the breaking of the code and things like that. And so, yeah.
There's just a quick question. Yeah. That is generally done also with normal classical computers and packages.
Yeah.
So what is that exact idea that makes it a little bit more enticing for us?
So enticing, I don't know, but then we go back to Richard Feynman, right? Like how did we even start quantum computing? He said that, nature is quantum. So if you want to simulate it, you have to have a quantum device. And so, we are able to simulate, at the atom level, at the molecule level. So we can come up with new, structures, which otherwise you will not be able to do if you're not able to go down to that level of simulation. So
every quantum algorithm is going to be better.
There are only a few quantum. Oh, come on. Now, why are you asking me about quantum? Yeah, you have an expert here. But then if I were to answer that question, I'm sure we both will agree that there are only few quantum algorithms which actually have some advantage over classical. And that is why we should have more quantum algorithms happen. But those are also enough to give us a reason to build these machines, right? So that is how I would put it. And then, of course, we have India. With its oil producing regions here. So what am I going to get here? So what do you want to do? You want to detect new oil reserves, maybe. You want to detect and locate gas leaks. These are all interesting problems in oil and natural gas industry. And so this is done using sensors, of course. And the idea is that by using quantum mechanics, we can come up with sensors which are higher precision at certain instances than the ones which we currently have. And this is actually a use case that is being done in different countries for this purpose using quantum sensors. So it's not nothing is fictitious. So this is an actual device. It is a turnkey, transportable, and easy to operate quantum sensor. It is sitting on Mount Etna, and it's giving you the absolute quantum gravimeter value. So instead of a human being sitting there and waiting for a volcano to erupt, which may not be the best way to do this, there's a device sitting there, and it's actually giving you real-time data. So this is the whole idea, just in a nutshell over the last 10 minutes, as to why we have this renewed excitement for quantum, in spite of it being one of the oldest fields which has given a lot of practical applications. So there is reason to be excited. And there is enough reason to be excited that we don't need to hype anything. Even without hyping anything, we are doing fantastic things as a community. And so this is what I think, is important for us to realize. But sometimes it gets a bit hazy, the line between what is real and what is not. So which brings us to the National Quantum Mission, which Vijay kindly already introduced. I won't talk about the resource availability in this mission. It's beyond my pay grade. But what I'll definitely say is that these are the things I work on long distance quantum communications, and then, of course, multi-node quantum network with memories, which is the technical group that I will be leading under the national mission. So these are the hubs that are getting formed. And the whole idea is that this is a field in which we want to see over the next few years a vibrant ecosystem emerge with industry, academia, and different players coming in, and a more mature technology emerging over the next few years. So with that, I go on to photons, which is what I promised to talk to you about. And of course, I love this cartoon here. It's you might have realized by now that I do not always take everything very seriously. It's a good idea to remain sane. And so along with antimatter and dark matter, and I think people here do represent these communities, so no offense to you. You have recently discovered the existence of doesn't matter, which appears to have no effect on the universe whatsoever. And photons are like that, right? They don't have mass, they don't have charge, they might not even matter. But that's not true. In fact, without photons, we won't be able to connect any matter. So photons actually matter a lot. And the next half an hour will be spent in converting the superconducting qubit people to photonics. That's the aim. So with that, I go on to photons. And of course, if you are not from the photonic field, which I believe most of you are not, have a look at this increasing level of complexity. This is a popular level article, I would say, but this is a textbook. Which my students and I wrote this chapter on photons and their applications in quantum, and you won't get it. So if you have to email me, and I can send you a copy as an author, but otherwise you won't get it for free. And so if you are interested, so this is what we are. We are the first lab in India dedicated to photonic quantum science and technologies, and we work on all these areas, as was said: quantum fundamentals, higher dimensional approaches to computing, quantum communications, and quantum sensing. And we have achieved a fair level of success over the last almost 13 years of existence now. So this is what we believe in. Today's science is tomorrow's technology, not so much the technology that is being referred to here, but then it's more like, we do a lot of work in the fundamental science and parallelly on the applications, so that, we have a bit of both. And because we're not engineers, so we just can't focus only on the applications. So we have a marriage in the lab of these two things. So this is the nutshell. In communications, we work on quantum key distribution, teleportation, relay, and repeaters. This is what leads to your repeater network that we discussed, which I already mentioned, the random number generation stuff, which I'll talk about, and integrated photonics-based quantum communication. So chip-based devices for this as well. In computing, we are looking at an interesting spatial photonic platform. I'll tell you a little bit. And also, I am a member of the JESDA Open Quantum Institute Advisory Committee. So that is, an institute which is looking at use cases for quantum for the Sustainable Development Goals of the United Nations. And we are looking at quantum enhanced imaging as an application for quantum computing there. In sensing, we are looking at imaging using entangled photons and also generalized measurements towards enhanced imaging. And of course, precision tests of foundations of quantum mechanics and quantum gravity as well. Recently, Gautam, wake up. Okay, so with that, this is the nutshell of how things look when we are photographing them. Very nice, no screwdriver, almost no screwdriver, but then otherwise it doesn't look like that. But then have a look at the website if you're interested in what we do, because I'll only cover this much. But this is what I would like to definitely say, that without people, of course, there's no lab, and I'm very privileged to be working with all sorts of people here. This guy is actually a master's student from Iran who's with us. So it's a very interesting, eclectic community we have of people. And so these are the current and these are the former people who have come and gone. And we also do a lot of work in collaboration with others. And most of it is theory experiments. So we have a lot of collaborators who are theorists, but the experiments are happening in our lab at RRI. And so this is more or less the big picture of, both India and abroad. We do have a lot of people who we are privileged to work with. So this is the video which was playing before the colloquium. And so I think, just for people who don't work with photons, so this is how we create photons in the lab. Because, we have a crystal which has a very high nonlinear coefficient. And then we have a laser beam which is incident on it. And of course, I'm simplifying it. It cannot be just any laser beam. But just if you have a blue laser, it gives rise to a pair of photons, 1 in 10 to the 8 or 10 to the 10, which actually, if you solve the equations, they come out in the form of a cone. And so if you take a cross section, there will be circles. And so that is actually an image getting formed as we speak. And soon we will zoom into an actual image from the lab, which is this one. And so that intersection point that you see there is what, could belong to either of the cones. And that gives you the entangled state because you don't know. This indistinguishability is what gives you the entanglement. And there are different ways in which you can generate this entanglement. And so this is just a little bit of a virtual lab tour for one photon source, just to give you an idea of how things actually look in bulk. And of course, we are also doing a lot of fiber and now also integrated photonics, but this is the standard way. And that is the nonlinear crystal, which this is the nonlinear crystal. You can see the pointer is interesting, but then you can see that is a nonlinear crystal. And so, of course, you will never see the photons, but the photons will come out. And so how will you know the photons exist? Because, why will you believe me? So 2 photons will come out. And these guys, they will come out at the same time, as opposed to human twins who come one after the other. And the photon twins, they come out at the same time. So they hit the detectors also at the same time. And they are called coincident. And so by measuring a coincidence peak, you can actually figure out that you're dealing with the right set because you have many photons which don't belong to the experiment that you were trying to do. And so then the emergence of the coincidence peak is what you see here. We've just taken some data. So we are looking at a 100 milliwatt laser here, the one that you saw. But then, of course, we have things which are higher and lower. It really depends on the application.
And these are picoseconds or
no, this is actually CW.
This is CW.
But then we also have pulsed.
Pulsed
sources. Yeah. So we have around 8 or 10 photon sources for various experiments, which we will talk about. But this is just to give you a picture of, how things are. Oh, sorry, I used the mouse. Now, will this work? It does. Excellent. Okay. So this was a snapshot and so some publications, but then I will skip that because we'll anyway do it. So now I go on to one experiment that I wanted to talk about a little bit because I believe that this will transcend physics and appeal to our diverse audience here. Going back again to the Nobel Prize in Physics, which was given to these three gentlemen for these experiments. So now they did what is called a loophole-free test, right? A loophole-free violation of the Bell inequalities. Of course, this is not the time and place to explain what are Bell inequalities because that's a whole talk by itself. But what I can say is that if you have a pair of entangled photons and if they are separated from each other, then if you measure what are called these Bell inequalities, if you violate these Bell inequalities, then you disprove what is called local realism. Okay, and so you just accept it if you're not from the field, that you disprove something which basically proves the underlying theory is correct, which is quantum mechanics is one possibility for such an underlying theory. So now what is a loophole? Now who looks to me like a legal, Gautam Dhagan, because I know you for the longest, right? So suppose you and I are fighting a case in a court of law. Any guesses who might win? It's obvious. You're just, yeah, he's probably just the politest person I know. So, he'll just give up even before he starts fighting. But then let's suppose we just, argument's sake, we are fighting. So what are we doing? So you come up with a set of arguments. I find a flaw in that. I come up with a set of arguments. You find a flaw in that. Just imagine you're doing that. Ultimately, I will win because I will come up with a set of arguments which is flawless, which is loophole-free. So that is the idea of a loophole-free scenario where there is no flaw. And so a Bell inequality experiment, which is loophole-free, is beautiful because, of course, the underlying theory is fine, but the last line is important, that it gives you a system where an eavesdropper cannot come and tamper. Because what will an eavesdropper do? Try to use one of those loopholes to come up with some attack. There is no loophole. So you have perfectly hack-free communications, right? And so this article, which I did not write, which is also very beautiful. Please have a look at it if you're a student, for instance, because it tells you about why loophole-free tests are important. And so now this is the importance of a loophole-free. It actually gives rise to our whole field of secure communications in a whole new way, because now we have something where we can't find a flaw, and flawless arguments are good. So this is our experiment in 2022. We published this. It's a loophole-free interferometric test of macro realism using heralded single photons. So what does this mean? So I will, this was the first ever such violation. And so this is what Vijay referred to, is what is called the Leggett-Garg inequality, which is named, of course, after Sir Anthony Leggett and his then postdoc, who's obviously not a postdoc in this picture, Professor Anupam Garg. They came up with the Leggett-Garg inequality. So it's the time equivalent of the Bell inequality. Bell inequalities, if you recall, I said there are two or more particles, let's say two for argument's sake, which are separated in space. So, fine. So that is why the non-locality and all that comes in. But suppose you have a single particle. What do you talk about? How do you say whether it's quantum or not? Is there no test, foolproof test to prove its nature? What about realism for that single particle? That's what these people discovered, the Leggett-Garg inequality. A single particle will move forward in time. So you can come up with joint time correlations instead of the space. And so that is the Leggett-Garg inequality. So for 30 odd years, people have been trying to do the loophole-free Leggett-Garg inequality. And we are, of course, very happy that we were the first lab to do the loophole-free violation of the Leggett-Garg inequality, which is similar to the Bell. Yeah.
Bell's inequality always has the loophole of statistical independence. Does the Leggett-Garg inequality also have that?
Now, Leggett-Garg inequality is nice because it's a single particle which is going forward in time. So we have, so I will discuss it a little bit, but we have what is called the no signaling in time condition, which means that, once you have gone forward, you can't be in any way statistically related to any earlier time ensemble. Because, of course, that is the underlying condition for what is called non-invasive measurability. It's a little bit of a technical detail, but then if you do not satisfy non-invasive measurability, then you cannot violate Leggett-Garg inequality. So which basically means that a measurement cannot disturb anything in the future or past. So this is called the arrow of time. But maybe we should discuss this a little bit offline because it can get a little too, I might digress a little bit from the main flow, but so we'll discuss this offline. But then it's obviously a very good question because that differentiates the two and gives us an advantage here in terms of Leggett-Garg. So this is what we did. And then, of course, more recently this year, we used this for generating device-independent random number generators. So I said that, once you have a loophole-free test, you can use it as a perfect test bed for different applications in quantum communications. And so this is a very important application because if you have a very good random number generator as a seed, then your entire security becomes better in a simple way because the seed is very important. And so this is a whole new paradigm in random number generators. And so this is the state of the art with the Bell. So Bell inequality violations have been used for generating such device independent randomness. And so this is what you see here. So what people started doing, and that was, you see that, they don't even mention the rate and so on. But finally, they started going this 200-meter separation because if you don't do that, then you have the locality loophole. So if you're not outside each other's light cone, then you can always influence each other. And so that closure started happening a little later in this story of Bell. Whereas in our case, where of course we have very appreciable number of bits and rate, we have generated this where the spatial separation is irrelevant. Because, it's a single particle. So now if you think about a device which is 200 meters long, it's a little difficult to come up with a device aspect of it. But in our case, we actually have a prospect of making a portable device, which will give you this kind of randomness, which is, of course, what is the benefit of our method over the whole Bell story for the same kind of randomness generation. So this is one example that I wanted to highlight, and this is us with Tony Leggett. We celebrate, and in fact, I think you were there for this conference, right? The last time he came to RRI, where we discussed this experiment when it was still ongoing with him, and that was very nice. And we got some recognition for it, and especially the New Scientist article, which called us the most watertight experiment of all time. So in India, of course, we have this thing that, unless people from abroad tell you that you are doing well, people don't believe you, even if it's published in a good forum and all. So I think this is what this article did for us. We have the blessing of a very popular forum from outside India. So very nice article, though, irrespective of what they said about us. So, so this is that. So going on to quantum key distribution, which of course is one of the key ideas in quantum communication. It is in fact the most quote unquote practical quantum technology because there are lots of companies making products and devices. So it's a very high TRL field in our, now this language that we have all become used to. Why you should worry about it? Now I look at, the younger folks there because you see, today of course is 6th of, what is it, 6th, right, Vijay? Because of course yesterday was the election, right? And of course, today we see the aftermath of what happens in an election. And I am sincerely hoping that, there was some error in how this happened. But then if we had quantum communications, maybe not, right? So this is the idea. So if you want to have a strategic communication of some kind, you need to do this differently than me shouting at you, because there's nothing strategic about what I'm doing here. But then if I want to, the little money that Sushil and I have, we don't want to lose it in an online banking fraud, for instance. So these are all areas where you need to be careful, where you use what is called cryptography. So you have your information, you encrypt it in a key, you have the information, suppose you're the intended party, you decrypt it, we are good. But Vijay is the eavesdropper and we don't want him to have the key. And so this is the general idea. And we discussed a little bit about why things are getting compromised even earlier on in the talk. So these are the standard ways. This is encryption, decryption, very famous thing much before us. So this is Second World War. This concept is way older than all of us here. And it has been going on. But then, of course, we did discuss the problem is that we are using something as the basis which can be broken. That is mathematical hardness. And so that is what I motivated earlier. So I'll skip this for the interest of time. And I'll just go straight to, so this is a snapshot of the kind of, anyway, again, a little detail. So why is it secure is an important question. Eavesdropper tries to do something, we will know. Because of the various protocols, which I will of course skip because of keeping it at the level that I don't want to get into the protocols. But as soon as we know, we will ditch that run of key distribution. And so we will only retain the keys where we know there is no eavesdropping. And of course, we have a threshold up to which we can accept also a little bit of error and all that. And so that is why it is not, I won't say it's unconditionally secure. I'll say it's information theoretically secure, because unconditional is a word I don't think I have the audacity to use. But information theoretically secure is how far I'll go. These are all, this is a few years old even. And so already we have all these very interesting products available for QKD. And this was the market trend that was done 10 years ago. I mean, and already I think we are looking quite a bit into this becoming reality. Okay, so what do we do? Of course, we work on quantum key distribution, but the focus area that we have is increasing the distance over which we can do this. Because, in this room, if I do quantum key distribution, it's fun, but it's not very practically interesting. So if, for instance, the new president of the US wants to talk to our current prime minister, then they might want to have a secure line and so on. So that is a long distance. And so now Gautam will ask me the question, what is so big about long distance? Because aren't you talking to your colleagues in Italy tomorrow? Again, Italy, ICTP, you get the point. Okay, so but then the point is that will fail. And so what is the big deal about long distance quantum communication? So this is the idea. If I were to keep on looking at you and you go further and further away from me, 100, 200 kilometers is fine. But beyond that, we all know the Earth is not flat. And so we won't see each other because of the horizon. So free space, distance limitation. If I use fiber, which is the common technology, every certain distance, there is a loss in the fiber. So what do we do classically? We actually put a classical repeater. So we boost up the signal. It's a word we also use in our everyday language. We can't do that in quantum because of no cloning theorem. We can't copy an unknown quantum state. And so we have a problem that we can't do the usual things we do. So we have to do unusual things. And so these are some of the unusual things that we are doing, and so this is one of the things where we have these long networks with trusted nodes. This is the weakest unusual thing to do because, of course, it is the most vulnerable. If one of the nodes gets compromised, the whole thing gets compromised, but we will still, of course, show it as a part of NQM. Then comes the hard one, which is the optical fibers, but dark fibers usually. Now then comes the memory-based entanglement distribution, which is the hardest problem because that is at an R&D level globally. But if we can manage to do that, then it's really secure because entanglement is truly random. And so we have that to our advantage, which is what we are going to do under the national mission. And then we can use a satellite as a trusted node also to increase the distance, which I will show you a little bit because we've been doing quite a lot of work in free space quantum communications. So again, for the students, if you're interested, some of us were almost forced to write some of these articles after the NQM was launched, and they're not half bad. Even his is good. Mine is better, but his one in quantum computing is also not bad. So you can have a look at all these articles. Okay, so having said that, what do? Well, we are working on India's first project towards satellite-based QKD, but we don't know what's going to happen later. We have done all the ground-based milestones, but now what happens under NQM is anybody's, So there's a lot of territorial things going on. We will see what that means. But we have done quite a lot on Earth, which is within our controls. And integrated photonics as well, quantum teleportation and DI-RNG, as I mentioned earlier. So this is the name of our project towards satellite technology, which started in December 2017. And so, it was basically, we got the funding from ISRO for developing all these ground-based milestones. And so why is this experiment exceptional? Now, by now, you've listened to me for half an hour. Maybe you'll say because we are doing it, right? But then again, I won't take that as the formal answer. It is exceptional because we started this experiment when quantum was not that big a buzzword. And in fact, we got the funding after our neighboring country launched the first quantum satellite. And then we were asked the question, how come we are not already working on this, right? I said, we proposed this 4 years ago. Theek hai, we got funding. So this is how, I'm very grateful to the neighboring country, which I won't name, because at least they made it real for us from science, science fiction to science. And whatever we have achieved, under this umbrella of free space, I think, has played a small but significant role in making all this real for many of us, the whole ecosystem. And so, of course, security part I will skip because you already got it. So this is the idea. So you can have an entangled photon source in your satellite. You can send the 2 photons to 2 different ground stations, and you do many more things, then these guys get linked. So this is what is called downlink based QKD for obvious reason, because the photons are going down towards the 2 ground stations, right? And so this is what the Chinese satellite demonstrated, very nice papers, which you can read if you're interested in it. So what we want to do is what is called uplink based QKD. So again, the difference is my photon source is on Earth. I don't send it up, okay? I retain it in my ground station. So this is the kind of thing which has not been shown. So there are 2 reasons why we want to do this, because we have 1 life, and is what I believe, although cats have 7, but then we want to do something which has not been done before is a nice thing if we can do it. But then more importantly, it actually has scientific advantages over the other method. And so what is that? That is because you see the photon source is the only quantum thing in this whole thing, right? Everything else, encryption, decryption, post-process, these are all classical. So it's the quantum source which gives us the quantumness in the whole thing. So that remains with me. If that guy flies away and something happens, will I be able to pull it down like a kite? Maybe your balloon, you can pull it down a little bit, but then it's not going to be high enough, right? So it's not so straightforward to just keep flying things economically or otherwise. So I have my source with me on Earth. Then, of course, I can change it. Now, tomorrow, Sushil comes up with a better source. I can, replace your source with mine if it matches certain wavelength conditions, maybe brighter, maybe more bit rate. I can't do that if it has flown away. Third thing is I can include quantum memory, because, the whole idea is not just about satellite or memory. It's about bringing it all together, which is called the quantum internet problem. So you use memory-based entanglement distribution, and you connect that up with satellite so that you can have the longer distance. And so the whole globe gets covered with this quantum communications network. And so that is going to be much easier, because already the memory research is probably at the most R&D level globally. So to have a space compatible one is a future project. So this makes it much more real and on Earth, literally. So it gives us a lot of scope for doing things. Yes, Sushil.
Do we have an idea of what kind of collector efficiencies can be mounted on?
Yeah. So I can give you those details after the talk, because we have a paper on that, which I will show you. Yeah, we know exactly what to do.
So,
yeah.
The satellite is just behaving like a mirror?
No, it's not behaving like a mirror. Satellite is behaving like a courier.
Receiver.
It's a receiver. So basically it comes on top of my ground station. I do some, key distribution. Then it is moving in its own orbit, and I don't see it anymore, but you are sitting somewhere else on the planet. You see it when it comes on top of your ground station. You do the key distribution. So there's a key 1, there's a key 2. I can use key 1 to encrypt key 2, as a result of which you and I have one key which we share. So there is an XOR operation and all that, but then so that is the idea. So I have actually 2 entangled photon sources that are required here, one in your case, one in mine. Whereas in that one, there's only one. But then if you see, if I'm sending it down, I have a solid angle problem. Or at a certain height, I can only send it to a certain distance. Then I have to go higher to send it longer. But here I don't have that, because I'm not doing it simultaneously. So it could be 13,000, 14,000 kilometers, doesn't matter. So this is the general idea. And so these are the logical flow of events. So of course, these are all the things you need to do inside the lab. And so QKD, single photons, different kinds of protocols. And I will show you some of that. And these are, and so this is just a snapshot. If you wanted to take a picture of what are the things you need to do towards the satellite QKD project. But then, of course, where are we in our journey? We have done all the ground-based milestones. Okay, so we have done everything that we can do on Earth. Now we have to basically look up and see if somebody can give us some space in space. We don't know that.
We have fly the detectors.
We flied it, not just detectors, the whole payload. But you're right. So this is a problem, because space compatible detector is a technology which is slightly different. And so the NASA, they have come up with, they just flew one a day before yesterday, actually. Thomas Genevine from Waterloo, they flew a payload which has such a detector. So it's some research has happened. And then, of course, currently we are making the lab model for the payload. And then if we get any blessings, then we will be able to do the satellite part of the project. Okay, and so these are our milestones, the first free space experiment within the lab. Now, one thing Vijay and I were discussing earlier that, just because somebody has done 1,000-qubit machine doesn't mean that tomorrow he'll come up with 1,000-qubit machine, because you have to start with 1, 2, 3, 4. There is a process, and only then you will reach a certain number. So you can't just look up to the satellite. You have to start with the ground-based milestones wherever you are. And so this was the first free space experiment we did, and this was the first one that was published from India. Nice results and so on and so forth. Then the first demonstration between two buildings at RRI, and this was also the first one from an Indian standpoint. Likewise, this was very important. This we did in March 23. We had a stationary source and a moving platform, which we were able to talk to and do QKD, because satellite moves. And so that took us a couple of years to develop this technology. And then we also did software development, which I will talk about a little bit, and many other things, which I will skip for now, because I have around 12 minutes. Yeah, because, suppose classical technology fails me. Okay, so this is just, if you're interested in all these milestones, then there are certain references which you can look at. So this was the paper where we reported the first free space experiment. This is how it looks generally also. So now I wanted to talk 1 minute about the software that we developed, which happened out of serendipity. So essentially, when QKD is becoming very commercially viable, so people are coming up with protocols. So how do you test them? Do you buy all the components and set up a little lab and test them? That is quite expensive, and we may not get the funding. It's not straightforward to just receive that funding. So can we come up with a software where you can, simulate this realistically? This was the question we were asking when we were setting up some of these experiments. And so we came up with many different available softwares online. But what they don't do is, they don't actually worry about QKD being a real experiment. So what happens in a real experiment? Your physical processes are not ideal. Your components are not ideal. So software for QKD is developed by software developers, no offense to them, but they don't do experiments. So 50-50 beam splitter is 50-50. Detector is 100% efficient. So then the results don't match as well as they should. And so we came up with, we say that, we are going to have precision from imprecision. So we are going to put in all imperfections and come up with a perfect software. And that is how we became software developers, for no fault of mine. And that is what led to QKD Sim, which for a long time used to be a logo without a company. But the last 2 minutes, I'll tell you about a company as well. Okay, and so this is now a little bit of detail. So we follow what is called the Agifall model of software development. So I'll skip the details of that, but this is the idea that, this is the Agifall. So essentially we have many modules. So it's a waterfall structure, but if you come up with a better module for something, I can replace it without replacing it top down. So that was the idea. And this is the result, which is important. The experiment and simulation matching was way better than from these available commercial softwares. Okay. And we, of course, wrote lots of algorithms, which I'll skip. And so this is important that, this was the previous result, this classical technology. So this was the previous result. So for QKD, this Q-bar has to be low because that's error, and key rate has to be high. And so this was the original, record from a group in NASA. And so we actually beat that record with our experiment in 2020. And we did that by using certain salient features, which is a bit technical. So I will probably skip that. Received a bit of recognition from popular media and, of course, Government of India. It's getting recorded. So the Government of India recognized us in 2020 for being one of their 20 success stories, which we are very proud of. So very rare. And we also got a patent for the software, and it was RRI's first quantum technology patent. And now we have 2 more, which are getting, reviewed. It's being submitted. So, and this is another thing which is of interest perhaps to Sushil, who's actually in the field, right? So, when you have this long distance communication, you're interested in decoherence problems. And that's why this is interesting perhaps to you, that your polarization degree of freedom, it can change. In a fiber, it gets scrambled anyway. Even in free space, it can flip. So how do you deal with this? If you're talking to a satellite and if things have changed, then what do you do? It's a real problem. And then another problem that is of interest to my colleagues from high energy physics is that there is a difference in reference frame. A satellite and Earth are not in the same reference frame. So there are these interesting problems which come up. Okay, and so people, of course, have discovered this problem before, but then this is our experiment. So this is the idea. This is a significant challenge. And what do people do? They do what is called active feedback. Okay, so you have this, you send another beam, which you use to characterize the channel and use that information to change your state. Because your state would have changed because it was HH plus VV, but because of this thing, it changed to something else. So you change your state back and then you do what you need to do. So this is quite resource intensive because this also sometimes is using robotic arms and more things have to be used in that channel to characterize, then use that information. What we did is a passive feedback. We said, okay, we live with what we have, our state has changed, but because of LOCC, which is a theorem which tells you that even if there is an unitary rotation, the amount of entanglement does not change. Local operation in classical communication cannot change entanglement. So we use that and said, okay, the state has changed, let me change the measurement basis. Instead of measuring in the plus minus HV basis, let me rotate that because then I don't need to put in any more resources. And that is the passive feedback. So, oh, that is the whole paper. So of course, that so you do a thing called quantum state tomography. So you can find out how much your state has changed. And then there's a lot of theory which we can discuss offline. Basically, you come up with a mutually unbiased basis, which is corresponding to that rotated state instead of the original one that you had. And then it works beautifully. You don't have to spend any additional resources for it. And so this is what we showed. And I'll show you one graph.
Active thing, active correction, that active feedback that you do. Not you guys, but if other people. So is it time consuming or this one? Which one is economical in time?
Now, these are two separate questions. Time-wise, we are not as good yet because we have to still do a tomography. And that is what we are working on actually to try and figure. But economically, we are good. So in fact, your question, we are good from the economic because we don't have to spend anything else. But here we are taking a little more time. And so we are actually actively working on that. Okay. And so, but then this is the graph I really like. So I like to show it. So if I didn't use the method that we are using, then my error would have just shot up like that. Okay. As my state fidelity decreases, the error would increase. If you don't do anything to change the basis of measurement, it will just keep shooting up and then it's nonsense. Beyond a certain point, it doesn't make any sense. But using our method, we have the orange graph, which holds it perfectly below the information theoretic threshold of 11%. And so it works beautifully, actually. And so this is something we were very happy about. And so lots of...
Although it is low, it's still okay for the satellite angular.
No, at the moment, of course, we have tested it. Now, next thing I'll show is we've tested it across the free space link.
Okay.
Well, it will be obviously applicable to, but then, satellite has an 8-minute pass.
Right.
And so we are a bit concerned that we are taking a bit too much time for it to be applicable at that distance.
Okay.
And so we are doing things to,
Gotcha.
make it better and better as we speak, right? Otherwise, of course, active feedback is anyway there, but this is actually nicer because it's always nice to actually spend less on a project for various reasons, but also physics-wise. Yeah. And so I will go on to showing what I showed you. So this is a video which also usually plays, and this is just basically to tell you about how free space QKD actually looks without going to my lab. So this is the entangled photon source, and one of the photons, is going to hopefully remain within the lab. I forget the video. Yeah, it is within the lab. And so this is what we call the Alice measurement station. Alice is, of course, not a person, it's a measurement station. And the other guy moves out of a telescopic arrangement through a hole in the window, literally, across RRI campus to another lab, which is also our lab, which we call Bob Lab. And so enters Bob Lab and goes through his or her, we can make it gender neutral, measurement station. So this is the general idea. So Alice remains within one lab and Bob is across, or whatever you want to call it. And so this is how we did this in February 2021, actually, this free space experiment. And now we have shown, so just, and we got a little recognition for it, but this was important. Of course, once we did it, another institute came up with, it became a war of distances. So at RRI, some people you are from RRI. How many meters can you move without hitting a tree? It's a math problem, right?
We pride ourselves on the number of trees.
Yeah, we have more trees than humans on campus. According to C.V. Raman's will, it should remain like that. So we have historic reasons to have trees and humans in a certain ratio. Or in other words, 50 meters is the best we can do without cutting a tree. Okay, and so we actually cut a branch, but that was allowed. But then, of course, another group came up with a 100-meter thing and claimed this is the first time in India we have done free space. in small caption, 100 meters, because it was not the first time in India that they had done it. So this became a very weird thing for us because, so many people were doing things for the first time after we had done it for the first time. So then we said, okay, we answer this scientifically. We simulate the whole thing. We can't cut trees, but we can, of course, do physics again. So we tell you, how far we can go with our current setup. And it is way beyond the 100 or the 200 that you will hear as you read newspapers, because they don't have papers per se. And so then you can look at that. But so this is what we did, and this was a very rewarding result to see that things will work very well in the kilometers as well. But if you go to many kilometers, then you will have to change the optics. And you know that, right? So you'll have to change the optics and get the collimation correct. Oh, yeah. So this, of course, now if you ask me exactly, then I'll take more than 1 minute. But I will show you the paper where you will find it, which will come up. So, and so we did that, and then I wanted to show Sushil this result. So this is the result from the free space experiment and the MUB, this, approach, passive feedback approach, which also worked very nicely. That is the, you can see the red dots and the below the 11%. So that was the corresponding orange dot that you saw in the previous one. So this is the free space experiment, and also this worked rather well. And so we will skip the details of this and go on to, and we actually simulated all the atmospheric losses, which was a hard problem. And this may be of interest to you. And so this is the development of the pointing acquisition tracking system. So I'll take 7 more minutes. Yeah, because I have one, but yeah, okay. So as I was saying earlier, that all this is fine, free space is fine, but one of the things ultimately has to move, because you have to. So then I have to point towards it, track it, and acquire data from it. And that is called PAT system. It doesn't happen in a PAT. So it took us 2 years to develop. And this is the various stages of development, actually. I'll skip the video. And so this was interesting because, we actually got a circular, sort of, so that's all done at RRI workshop, by the way. So we actually got a circular arc simulated, and we were able to do the correction and all that. And so then finally, we went on to do this using this guy, which is our moving bob. And so now we have the 3rd version. So this is the version 1 that you see. So it has all the optics, optomechanics, synchronization that you need to fly. So this is the payload in a large form. So we need to make it smaller and space compatible to actually fly it. But this is the smaller version of this. This will actually fly. Yeah, smaller, and of course things have to be space compatible. And so this is what we did, and this is to give you a reference for the size of the object. And so, and this is the paper that you may be interested in, which actually tells you about how, how to deal with atmosphere. So the static and dynamic components of atmosphere, turbulence included, and how to come up with the simulation for the telescope sizes. What is the, collection efficiency, as you said. So this actually it's a rather long, detailed paper, which you can have a look at. So this is that. And this is the thing we found, that, we just took up 3 ground stations whose data was available online, because we, of course, didn't get any data from anyone. So we took the publicly available one and found that, of course, the highest one is best one. So if you actually set up a ground station in Hanle, it'll obviously be nice, because it's also proven now physics-wise. So it's a very nice space for such experiments, and a little bit of our appreciation. Now, the last 5 minutes on things which are not quantum communications, just to tell you that we just don't communicate. We also do some other things. So this is the quantum computing. And so, as I was saying, what we are doing is we are using what are called the spatial bins of photons. So now I think maybe I have So essentially, we deal with qubits. A lot of us, many of us work with qubits. But if you want to have 4 states, then you need 2 qubits. But then if I have a q quad, which is a 4-dimensional state, then I can deal with 1. And so this is the general idea of what is called a qubit-based system. And so we are looking at photons and qubit architectures. And I don't have much detail because, it's going to be a rush through. So we are using the spatial degree of freedom of the photon, and we have already shown bipartite qubits in the lab, which are also nearly maximally entangled, and done very interesting things and protocols with them. Now we want to take it to higher dimension as well. So this can easily scale to 10 cross 10. So 2 to the power n is interesting from a qubit perspective, but 2 to the power 3 is 8. 3 squared is 9. So 2 qubits has the same complexity as 3 qubits. And that is why we want to keep increasing the base to the extent possible so that we can reduce the exponent, because it's always harder to increase the number. As we very well know, numbers matter. And so, and the other thing, so that is just a general idea of what we do. And if you're interested, we can talk more after the colloquium. We also work on cloud-based quantum computing. And so this is some of the results we had, where we use the foundations of quantum mechanics as a benchmarking tool for quantum computing. So the Perez test and the Sorkin test were used to see how these quantum computers are, and how noisy, how much can noise actually deviate results from quantum. And so this was testing the foundations, and this is using it as a benchmarking tool. So we did both the problems, and we did many other things which I'm not showing here, using cloud-based quantum computing. Fundamental tests of quantum mechanics is, of course, what I fundamentally like to do. And so this is a lot of things that we have done in this domain. And just to give you an idea, this is a very interesting one. So Hongo-Mandel is something I saw from your lab in QCMC. I saw the poster, right? So of course, we showed a Hongo-Mandel dip using classical light. And so this is something which challenges the textbook notion of Hongo-Mandel being a quintessential quantum optics phenomenon. So we showed this with classical. You can have a look at it, and interesting things we observed here again, which I'll skip. And so this is our series of work on superposition principle and bond rule using different kinds of slit-based experiments. So one, of course, we already talked about in the beginning. This I did at IQC, but after that, everything was done in India in our lab. And so these are all various theory and experiment. So this is a very interesting problem. It is a philosophical thing. So entanglement also dies. Okay, entanglement interacts with the environment, and there can be a sudden death of entanglement at a finite time. That's called the sudden death of entanglement. And so one of our problems, actually, we are also very interested in decoherence, is to arrest decoherence. So we have come up with a technique where we can manipulate this and make it not happen. And so we have very recently succeeded in showing this manipulation experimentally, which we are writing up.
Sudden death not happen.
Yeah, sudden death not happen, and also change the dynamics of entanglement. So something which was going this way can actually be delayed, and it can become asymptotic decay instead of a sudden death. So we can play with the dynamics of entanglement. And so these are some theory works where we show how, and the experimental work we have recently completed, which is getting written. And so that is that. And this is something which, again, I suppose some of you may have seen. This is a tool we came up with using weak measurements, where we can come up with an alternative to quantum state tomography. So just for biologists here, you know the CT scan. I think even non-biologists know the CT scan. But then, so the idea is that you have sections, slices, you put it together and reconstruct the image. That's what we do for a quantum state. We actually avoided that. We actually just measured an interference pattern and got the state out of it. So one shot, single shot quantum state estimation tool. Have a look at this. We can discuss more if you're interested. And this is a snapshot of various things we have done using weak measurements. More recently, the loophole-free demonstration of a quantum Cheshire cat. So Yaki Rahanov's Cheshire cat problem, where Sushil is there, but his head is here. No, not head, maybe hair. The hair is here without Sushil being here. So that is the idea of the Cheshire cat, grin without the. So we were able to show that using photons. But what is very important in our thing is that we were able to show it in a joint measurement. People have so far done one run and shown Sushil there, and in the second run showed his hair here. But we have been able to show it in the same run. So it belongs to the same particle. So that was a very important loophole we closed. And that was the first paper that you see there. Again, something we can discuss. And various things we have done towards proposing tabletop experiments for quantum gravity, which is something which is using these quantum information ideas, which we have established using this QDIT architecture that I talked about. And this one is a very recent one, where we have been able to measure this quantum measure. Now I'm looking at Gautam once more. So we have string theory, we have loop quantum gravity, and then we have the causal sets. And I'm not going to get into the argument of who's better. That's not my job. But if you are a causal set person, then you know the quantum measure, because the quantum measure is used as a basis for the causal set approach to quantum gravity. And that was discovered by Raphael Sorkin, who, of course, I think, irrespective of which camp you belong to, is respected. And so Raphael discovered the quantum measure, which is a very, very hard theory thing. And we said, nah, finally, let us work together and do an experiment where we can measure it. And this is that experiment where we have been able to measure it in the lab, and up to 13.3 standard deviations from the classical limit, which is actually a pretty impressive deviation from classical. This is our global quantum internet. It's a picture we always like to show. And as Vijay said, I have to, of course, tell you what we are doing. It's 14 TGs. There's a controversy whether it's 14 or 17, but if you ask DST, it is 14 apparently. And so we are going to do this, a multi-node quantum repeater network under the national mission, which fits in beautifully with our long-distance quantum communication ideas. Last minute on something that is a different hat for me. I actually have now co-founded a startup, which is called QSIM Technologies. And of course, the difference is that, the people involved here actually are from the quantum. Now, this is a person I think is more loved at TIFR. So he keeps appearing every 1 or 2 years. In my case, it's a one vast type situation. So, but then Anindo, I think, may have spoken here before. I'm sure you're familiar with him. So, we actually believe in what we are doing. Otherwise, we wouldn't really do it. We're too old to just do something for the sake of doing it. And so these are two young people who also believe in what we're doing. And all of us are trained in quantum, which is not a bad idea for a quantum startup, because it's not a common idea for a quantum startup. So, so that is how we are there. And so this is our catalog. So we have software solutions. QCrypt is a security solution. QSight is something which is getting released in December, which is an imaging solution. And hardware, we are going to actually form the portable random number generator from the patent and the papers that you saw. And photon sources, of course, we will commercialize, because that's something we kind of know how to do. So this is currently where we are. And so with that, why do I have a smiley? Oh, okay. I don't know. The smiley came before, but then this is just a bit of detail on what these products are about. If you're interested, we can discuss more. And this is the buzzword TRL. And so, of course, we have to say that we are not at 7. We are at greater than equal to 5, which is a honest thing. But we, of course, need funding to reach the 7 and the 8. I'm hopeful we will get that. And so if you want to work with us in the lab, outside the lab, in the company, come. Future is, of course, quantum. There is no argument about that. So I think that is my last slide. No, this is my last slide.
Thank you, Urbasi. Thank you for giving us a span of the work and keeping us engaged. So, questions for Urbasi?
So, more of a fundamental question about the QKD. So, as you said, that it's one of the more practical things out there, and like from fundamental idea of the principles, it's unconditionally secure from the information theoretic.
Yeah.
So, what I wanted to understand that today, are there technological loopholes in terms of how good a certain component is, which will actually give rise to potential ways to hack that system? Can you say something about that?
Yeah, so I mean, so this is the whole point of QKD SIM, right? Like, so QKD is, of course, based on actual practical hardware. And so we do have issues with the hardware that we currently have, not just we as a community. And so a beam splitter, if it is 4852, and suppose you are the manufacturer of that beam splitter and you know this, you have given it to me knowingly, 4852, then I've created a little bias in the zeros and the ones. So of course, the key symmetry may get affected by that. So that is why things like, QKD SIM come in, because they actually tell you what to expect from these various imperfections. But one thing, Vijay, is important is that this unconditional secure I don't like, first of all, as I mentioned, I would not want to say that. But then we also have security analysis for each protocol, which tells you up to what error is permissible. So it's not 0. So for instance, for the BB84 protocol, it's 11%. So up to 11%, whether it is an eavesdropper or whether it's an imperfection introduced error, we are okay with that much of error. But above 11, and this comes from mutual information based, very hardcore theoretical calculations. So the 11 is a number which you cannot change for BB84. For B92, it becomes 4.8. So it's actually harder, because you have to be even less error prone. So there are non-zero numbers for each of these protocols, up to which you can tolerate. And beyond that, you don't. And so once you have a non-zero number, then what we do is what is called privacy amplification and error correction, similar to the error correction story that we have in quantum computing. Then we can make it to a 0. But we cannot make it to a 0 if it is beyond the security threshold. It's not even a candidate. So that is why I said a lot of it is classical and algorithmic after we get the threshold. Yeah.
There's a question here.
Yeah.
Yeah, hi, my name is Dikshant and I'm a student in Professor Sushil's lab. I just had you briefly mentioned about your tabletop experiment for quantum gravity.
Huh.
And so I just wanted to like quickly just clarify if you're doing like precision experiments for classical gravity, or if you're actually using the theoretical concept of quantum gravity and using quantum mechanics to test quantum gravity.
No, that's a very good question. So, it is a tabletop experiment. Just to go back to it, because so it's a tabletop experiment. So read my title. It's a quantum gravity relevant experiment with photons. I'm not measuring quantum gravity. I'm measuring what is called the quantum measure. The quantum measure is this mu, this quantity, which actually is a probability-like measure, which, because of interference, can take on values greater than 1. And that happens because of the quantum nature of the problem. So if I'm able to measure this quantum measure, then of course I'm contributing towards, some kind of a, baseline, experiment which has something to do with the causal set approach to quantum gravity. But then quantum measure is what I'm measuring in the lab. As I say, measuring a probability, quote unquote, greater than 1, because the quantum measure is not the classical probability. It includes interference, so it becomes greater than 1. So I'm not measuring quantum gravity in the lab, because that you cannot do with photons, because photons are massless. So, but then the experiments I showed before, which of course are proposals, not experiments I have done, but I'm interested in doing them, actually talk about massive particles and how you can use these qubit ideas that I discussed towards quantum gravity experiments. So now that is a good question. It's basically entanglement-induced gravity. So there is debate on the nature of these experiments. Some people like it, some people don't, but that's science. But then if you can show that an entanglement is emerging, then the thing is, there must be something quantum underlying that phenomenon. And that is how these experiments are motivated. And Shogoto has been doing this for a long time. Such, proposals for experiments. Yeah.
Okay.
Thank you.
Okay. There's a question there.
Yeah, so that I didn't show because of lack of time. So what we are doing is, so if you have a single photon and it is incident on a plate which has, let's say apertures. It could be, for instance, slits, and so suppose you have 4 slits and the photon is incident on this. You don't know which slit it will go through. So the position of the slits becomes your 0, 1, 2, 3. So because you don't know what it is going through, you form the alpha 0 plus beta 1 plus gamma 2 plus zeta 3 state. So that is your, a 4-state system. So this is one way in which there is a lot of people have done that.
Is photons the only mode for the?
What we are doing is not that. Just to complete that story, we are not really taking it at the photon level and discretizing it. We are modulating the pump beam itself. So we are modulating the pump beam itself and generating the structure already for the pump to be incident on the crystal with that structure. So the photons come out as qubits. We don't discretize it later because it's better to deal with the pump, which is much stronger. Because, if you can see something, you can manipulate it better. Photons you don't see. So that is called the pump beam modulation technique. What was your second question?
Is photons the only mode to physically realize this? Like, is there any other?
Well, photon is not a mode. Photon is a kind of, photon is a photonic system, you mean?
A photonic system. Is it the only mode?
I mean, you have qubits naturally in superconducting systems. So, they have these various levels of the Josephson junction. And of course, if you just restrict to the first 2, then you have the qubit, but they naturally have other, and there is a lot of interesting work that happens in qubits in these systems as well. So no, atomic systems as well.
I have a question.
Yeah.
So you mentioned about this with entangled photons imaging. There is a lot of advantage, especially for chemical and biological samples, because you could go beyond the diffraction limit under certain conditions of how many photons could you entangle together. And have you tested these experiments in the lab? Because there was something written in the initial part where you said about imaging with entangled photons.
Yeah. So what we have shown, what we have played around with, I don't think this is one of our biggest research results. It's more a playing around situation where we have used entangled photons and shown ghost imaging. So ghost imaging, yeah, we have shown ghost imaging. But then going forward, actually, we have certain ideas in which, we want to use this towards somewhat more ambitious goals.
Imaging. Yeah, that would be great for materials.
Exactly, because I actually am very interested in biology.
Right.
I mean, everybody's interested in biology, but then, I mean, I want to bring in some elements of biology in what we do. And so this is more at a playground level.
Yeah.
But then, of course, we have shown the system.
Classical, the way.
No, we have
Marxism is
entire,
done Currently,
Yeah.
the technology.
but if you are actually interested in this, then I'll refer you to some papers from a group in Europe which who have actually taken this forward in a very interesting way. Yeah, from Germany. Yeah.
So coming back to these qubits which are spatial dependent,
Yeah.
how reliable are these qubits in long distance free space communication?
Yeah, we'll find out.
We don't know that yet.
No, the orbital angular momentum based
That-
approach,
okay, that's
people have already tested.
This
This
position
one,
based-
we want to find out because we have all the tools to find out. So that's one of our goals to find out. Yeah. Yeah.
I think we should stop here and let Urbasi breathe, and we can have a little bit of
Sure.
coffee and snacks.
This
as we
time
work.
it will also be available.
Okay, sure.
So I love our colloquium host. You know, even before I met him, he said sorry 4 times. So, but then
And you're keeping accounts.
it has been a lovely experience. So thank you very
Thank you.
much.
Thank you, Urbasi. Let's have a, yeah, and let's walk out together with Urbasi and ask more questions. Okay, thank you.
I just shut this off. That's okay, right?
Yes, that's okay. No, no.